All right. Good morning, good afternoon, good evening. I'm pretty confident we are now streaming. My name is Nate Chun. I'm delighted to be here. I'll be your moderator. But I'm really happy to get to introduce Bezler here today, yet another one of our amazing Java champions. I'm not going to steal too much of his time. We had a little bit of technical glitches getting going there. It's the beauty. We're doing it live. We're doing it live. So I will go ahead and drop out and turn the stage over to you, my friend. Good luck.
Thank you. Thank you, Nate. Hey, hello everyone. Welcome to my session. Basically, what I'm gonna talk about. Okay, sure. It's about virtual thread. But before going into that, I want to give you some background. So that's what it is. So let me, share the agenda bit. Basically, I'm going to go ahead with a bit of history of Java concurrency in general, like how it came, and then how what are the problem we had earlier before you know introducing virtual thread, and then there's other alternatives, and end of the in while I'm done doing all of those things, I'll introduce Project Bloom, which is basically virtual thread, and that's what we are excited about, right? It's JDK 21, and pretty much a lot of people, a lot of companies, and a lot of projects are using JDK 21, and even virtual thread. So it's exciting. Anyway, moving on. Um, so let's start with a context and a bit of history, right? So I think pretty much we all know it, which is it's not a overstatement, right? Java is made of threads. Whatever you do in Java, pretty much use Java. Even though, like, if you are a beginner Java developers, you don't see threads. You just write code from the main method, and then it just runs. It still uses threads in many areas, right? Now, questions gets to be what is essentially a thread is. In Java, threads are basically unit of execution. What it means is, you have a code, you have a block of code, or you have class methods, all of those things. So let's consider those as a block of code, right? And you want to run those in your computer. Who runs those code? In Java, a thread runs those code. So basically, if we have more threads, then we can run two threads. Let's say we have two threads. That means we can run two threads simultaneously. And it can those two threads basically run two unit of blocks. So basically, that's what it is in Java. Now, that means if we have more thread, that means we have more execution environment, right? So that's an amazing thing. That's what we want to achieve. And in fact, in Java, in many ways, that's what happens. For example, if you run just a main method, hello world program with main method, and essentially in the background, a lot of other things happens, a lot of other threads runs. For example, your garbage collection runs, right? GC is definitely done by a thread, and many other part of the applications. While JVM runs, other threads also run. So basically, that's what it is. Even though if you're writing simple, what do we say, hello world program, it's not that complicated, right? But we're still using Java thread. As you can see, this system out.println, this line is executed by a thread called main thread. And in fact, in all other areas, for example, a thread locals, debugger, profiler, exceptions, right? You name it. Pretty much everywhere threads are basically being used. So that's why you got to know about those things, right? Anyway, moving on. So this is how we essentially create threads. You know, Creating threads is pretty simple. I mean, I can just do it over here. If we want to, let's say, let's do a demo quick demo. And for P1 threads. So this is essentially our classical threads. This is what we have been doing before Java, before JDK 21. So let's start the, sorry about my typing, and time. So if we run this, these will, print in a different thread. And if I want to basically name which thread it is, then we can just print the current name of the current thread, and we can also set a name over here, which is JConference, JChampion Conference, conf thread. Anyway, I'm not sure this is a quite long name. It's going to print or not, but let me try. So as you can see, this hello method is executed by this new thread, brand new thread, right? So what happens is from this curly brace, a main thread is start, and main thread sees a block of code, which is basically creating an instance of new thread and then setting the name, starting, and wait. And inside this thread, we have just two statements, which is basically we essentially want these two statements to run by a separate thread, which is our JChampion conference thread. This is how traditionally we used to, create threads. Even though we use a higher level of construct, like we use a different framework and we use executors and others interesting things, but down those framework essentially use this construct. Anyway, moving on. The one thing we have to remember that in Java, which is we call native thread or classical thread, which is not virtual thread, basically. Anything that is not virtual thread, we can call it classical thread, native thread or platform thread, doesn't really matter. So this thread actually not a Java construct. What happens is it's essentially a mapping between operating system thread. So when we start a new thread, something like this, Java doesn't really create a new thread. It just, the operating system create this thread. This class is basically a wrapper around it. So we have to keep that in mind because we'll need that information in my future slides. Okay, moving on. Now the question is, these native threads or classical threads are quite expensive. There are few reasons for that. First of all, we cannot create as many as we want, right? There is a cap basically set by operating system. You can only create this much of thread, a native thread. And even though if we can create, if the number is large, let's say the number of native thread is quite large, it will take a lot of memories. And if our main memory is not available, then it will basically use the other sort of paging and operating system step. I'm not just going to go into that details, but what happens is if we have a lot of threads, it requires a lot of memories. And also that means we need to do a lot of context switching. That means, let's say I have 5 threads and we have one core or one CPU in our computer. So 5 of them will be context switching all the time, right? But if we have 5,000, then one particular thread will get less time, right? Because we have to do a lot of context switching and it has also overhead. So even though if we want to create a lot of threads, it's not going to help us in many ways. So that's why it's quite expensive, right? We have to keep that in mind. Now, there is a correlation between concurrency and throughputs. Why I'm saying that is basically, in our modern applications, so nowadays our application, especially the front-facing application, customer-facing application, requires a lot of throughput because a lot of user comes. Think about Facebook, right? Or a social media. A lot of user comes to this platform. So we need a lot of throughputs, right? The idea is basically if an application server can handle a lot of users, that's the benefit for us, right? That's how business boom, right? Now the question is, let's go to the implementation, how this works. There's the idea which is called request per thread. The idea is when we send a request to the server basically assign that request to a thread. And that thread takes responsibility of doing all the things it requires to send a response to the users. And it's easy, it's simple. Now the question is, if we use that model in our server-side programming, that means if we have more thread, we can have more we can serve more users. That means our throughput is high, right? And our operating system, in fact, can handle a lot of connections. from that discussion, we can conclude that if we have more connections, we can have more threads, and to have more threads, we need more threads in that model, right? But there is a but is which is threads are limited resource. It's expensive. We cannot have a lot of them. So essentially, this is what is the problem we are dealing with. So now the questions gets to be how many threads we essentially can create. I did an experiment with this simple code in my in machine that I'm currently using, and I was able to create like 16,000 threads. It has a lot. So this is the configuration of the computer that I experiment this and this code. It can varies. You can definitely try this code on your machine, and you'll see the different number. So basically, it's a cap that set by operating system, and yeah. I'm not sure if we can change it, but even though if we increase the number, it doesn't really help because there's other things associated with it. For example, context switch. So that's a limitation we have with our current situation. Anyway, moving on. So yeah, since we are dealing with modern software application development, we have a lot of modern problems. One is basically we are dealing with a large data set, while dealing with a lot of users, right? And we are also dealing with cloud cost, right? So if we have, let's say, the traditional thought process is if we have a server that can handle 1,000 requests at a time, then if we want to add more, if we want to serve more users, we can just add another server in the cloud, but that also has a cost, right? What if the server that we're using that currently serves 1,000 requests at a time, maybe we do magic and it increase a bit or more, like it let's say the number is 2,000. Definitely it helps, right? It's definitely lower our cloud cost. So these are the things, and on top of all of those things, so far we have established that the classical or the platform that we have right now are limited resource. We cannot have a lot of them, and we want to have a lot of them. That's one problem. And the other problem is, let's say we have only 1,000 threads available, and some of them are just waiting. Some of them are waiting for some things and doing nothing at all at certain time, and for a short duration. That's a waste as well. Let's say this is the classical server fan out we call. So let's say we have a request, and the request co- comes to this request handler, and we assign a thread over here to this request handler. Now this request handler probably going to do a lot of work. For example, it may goes to database, it may goes to the other web service or message queue, whatever it does. It does certain things. Now let's say for example, get, if we assign a thread, so if we do all of this, let's say we have 4 tasks over here, and we do them parallelly, and we only assign one thread over here, what would happen is let's say it will call the first one, which is a database operation, get call. And while it's waiting for the response, it's just wasting it's just sitting idle. It's just we're just wasting the resources, because this particular thread, which is expensive and we don't have a lot of them, are sitting idle and doing nothing while we're getting the result from the database. Similarly, if we have a lot of other calls associated with one particular request from user, that means we're wasting time in between. So this is what happens essentially. Think about this is a whole whole request. It sorry start from here, and it does certain processing, and the gray duration is basically waiting. and then it does certain other things, and then it keeps on waiting. So this is what happens in traditional scenario. Threads wait, threads stay idle, and if that's happen, we have a problem. Basically, we have a limited resource which is expensive, are sitting idle for no reason. So we can so if we want to improve our situation, what we can do is we can use those idle time to do other things, right? That will definitely help our situation. So to demonstrate whole things, I have devised a example. So let's say your application is basically to calculate credit. If you want to assign one thread over here, so what would happen is this all 5 operation is going to run sequentially one by one. So let's say first one is get person, it goes to database and waits over here. So this thread is waiting over here, and in second call, third call, and fourth and fifth as well. So basically, if we can calculate a time duration, let's say each of them takes like 200 milliseconds, and then the whole thing will take like 1,000 milliseconds. So that's a lot of time. And meanwhile, the thread was idle for a period of times. I would say significant of time. So how can we improve this situation? We can we can improve this situation if we could just parallelize some of this stuff, because for example, this get asset and get liabilities and something important work, they are not related. We can do in any order. So let's say we first call this get person and wait for the result, and then call these 3 things and wait for them. So if we in an ideal scenario, if all of them it can be done parallelly, then let's say all of them takes 200 milliseconds, and then we're going to do like the next one, which is calculate credits. So we are going to get, if we calculate all of them, some of the time duration, it's an improvement, like 400 millisecond improvement. And the thread the thread that was dealing with whole things now spend less time in waiting. So that's the improvement. So how can we do that? There's a classical implementation, which is basically using atomic reference. I just wanted to share that how we used to do and how we started improving. That's the thing I'm going to share over here. So basically, we'll create a new thread when you want to call this get person, and when this result is available, you just set on these atomic references. So if we just rewrite the whole things, it will look like this. It's a lot of code, but it does work, and it in fact reduce time. But over here we have introduced 3 more threads, right? Anyway, I'll get into that. But the initial thread, which is a responsible for calculate credits, is wasting less time now, right? So we can certainly improve this. This was a very classical one, but then we introduced like in Java 5, we introduced executors, which has future and callable, and from this code we can get to this one, which is much better compared to the earlier one. And we can create a thread pool, right? So what happens is first call will do the get person, and then we'll submit the next works. For example, 3 more works that can be done parallelly or in any direction, any order. We submit those in a thread pool, and then finally, when we are here, while in the calculate credits, by the time we are here, probably the result is already available. So we can continue on doing our work. It yields the same result, but it's a bit different and less code compared to the earlier one. So what essentially happens is in the thread pool, they have a blocking queue. Let's say basically takes task, and we have like a few number of threads available over here. So T1, T2, T3, something like that. It can be 100, it can be thousands. It depends how we basically define thread pool, right? So what happens is when we first call the get person, and then we call the get asset and put that task into the thread pool. So what does this thread pool do is basically take a task from the blocking queue and keep fetching, and it executes. And it gives me a reference over here, which is asset future. It's a basically a wrapper. It doesn't have the result yet, but it's a reference to me. And I can move on. It's a placeholder basically. When result is available, it will put that result into the future, like the atomic reference earlier we showed. So while main thread start over here into that request, and what happens is we call a bunch of feature. I mean, we submit some of the work into the thread pool, and while they are executing separately, main thread proceed and finally it can call this asset future.get. The problem is while main thread is here in the asset future.get, I mean in the last stage, if it is not finished yet, the main thread will still wait. But again, it's a bit of improvement. So moving on, while we are doing all this improvement, but we are not actually the ideal state. Future is quite low level still. It's not that high level. And like I said, we have still a get method, which is blocking. And it doesn't support composability option, right? We can not chain things which we like, right? I'm sure a lot of developers, like to chain things. It's a compose things, like in a functional way. So yeah, we're not improved that yet. So we need to do a few more works, and that's what we did in Java 7. We introduced a new concept called fork join pools. It solves certain problems that we had earlier. For example, in the thread pool, so we have a blocking queue, right? So each thread is going to take task from this blocking queue. So there is a possibility of contention, and so also there is a possibility of cache corruption. So those problems are basically solved in Java 7 in fork join pool. I'm not going to go into fork join pool a bit. I'm not going to go in depth in fork join pool because I need to share a few other things which personally I want to share. So that's why I'm just giving you the idea. It solves a lot of problems. For example, it solves the cache corruption problems. It avoids so what happens is it understands certain things. It does certain things intelligently. For example, it understands that some tasks are dependent on other tasks, and it use let's say in the pool we have 8 thread, then it will probably use 8 blocking queue or 8 queues, and also there is a concept called work slaying thread pool. Basically what is if a thread is his queue, one particular thread has a queue, and if this queue is empty, it can steal from other queue. Anyway, I'm not going to go into details, but it's improvement, huge improvement. And based on this improvement, which is fork join pool, we have got a few stuff. For example, we have got a completable feature which gives us composability. So basically we can now compose things. Over here, same things we have rewritten in a computable features, and then basically you can there is a tons of method over here. I guess it has like 300,000 lines of code and like 50 methods. You can do a lot of work with this. You can combine, you can chain, you can compose. So this is done on top of the fork join pull. Anyway, so this is kind of reactive in some way, rather than traditional imperative code that we used to do in over here. So in some way, it is more declarative as well. It gives us this nice tight boundary, and it looks good, but it also have downside as well. Anyway, we're gonna go ahead talk about that in a minute. Anyway, so what are the reactive alternative available in the Java ecosystem? For example, Raric Java, Vertex. These are the alternatives available. But okay, before going to but, same thing can be done using I have used Raric Java, same example. It yield same result, but it's a different way of doing things. It's more functional, and it has also composability as well. And the way all of these things done is basically try to reduce the waiting time, so that let's say we have 1,000 threads or 100, doesn't matter. We don't want to waste them, so we want them always working, so that way we can improve our we can have an overall improvement. So anyway, there's certain concept reactive framework as well. For example, it has learning curves, and debugging become difficult. For example, in your traditional imperative Java program, you can just put a debug point, and you can just debug something like that, and you will have a breakpoint and something like that. It's much easier. But in reactive programming, this debugging is difficult, because although your code is composed like that, but you never know which part of code running in which thread, and that also gives us a difficulties reading, finding the error. And if you want to see that stack trace, it's basically you don't have any clue from where to where it goes, right? So those are the side effects. And although reactive programming has some benefits, for example, the problem we are dealing with are basically solved by reactive programming in many ways, but we also have a lot of baggage. For example, debugging, stack trace, all those things are free in our traditional systems, but in reactive programming, those are a bit difficult. Anyway, moving on. So all those problem we had earlier are going to be in some way solved by Project Loom, which is basically a virtual thread. I'm gonna talk about virtual thread in next 20 minutes, and then if you have any questions, I'll try to entertain those questions. So how it is different from this traditional thread? So basically over here, we created a new thread like this, right? So virtual threads are not different in terms of API, what we see as a developer, but the creating virtual thread is something like that. Thread, of virtual, there is a nice builder button, something like that, and we can just call start a virtual thread, something like that. Sorry. Hello from the new virtual threads, and that's it. So it will start immediately, and we can have a reference as well. Join. So if we run this, we'll see a result over here. So as you can see, it prints hello from the new virtual threads. And there are a few other ways we can create virtual threads. Let me show you how we create, then I'll show you the differences. Okay, so that's one way. Since this one start immediately, we don't need to call, let's name it VT, virtual thread. So we don't need to call start again like we did earlier, right? We don't need to call it because it already started and there is a method over here. But if we don't want to start immediately, we can call unstarted method. Okay, same thing. And if we always want to start immediately the virtual thread, we can just use thread start virtual threads. Same thing. You just have a less keystroke, which is you don't have to write up virtuals. Anyway, so this is the new addition in the JDK 21, and since we have a nicer way of creating threads like this for traditional classic thread, which is we also call platform thread, has also similar construct. So we can use thread.platform, and then we have two kind of thread, which is unstarted and started. If we call started, it will immediately start. If we call unstarted, it will not start. We have to specifically, call this method, which is start. So now that we have two kind of threads in Java ecosystem, one is traditional thread, the other one is virtual thread, and what is the difference between them? Okay, and how these are going to solve all the problems we had earlier. Okay, so this is what essentially happens inside. It's a very high level things design. So what happens is in this part, the bottom box is basically operating system, and we have a over here the top box is basically inside the JVM, and when we do a traditional thread, which is platform thread, we can call it a carrier thread as well. Why I'm going to say, I'm going to talk about in a minute. So basically, when we call this traditional thread, it has a 1-1 mapping with the operating system thread, which is native thread. And the virtual thread works on top of this native thread or on top of this platform thread, or we can call them carrier thread as well. So we have a lot of virtual thread, and they are scheduled by a JDK scheduler, which is basically our fork join pull. What happens is when we create a virtual threads, it basically scheduled by our fork join pull, and fork join pull has a number of platform threads or native threads or carrier threads. So what happens is, let's say I have a fork join pull and it has 10 native threads or whatever you call it. So what happens is JDK scheduler basically schedule a virtual thread. So it takes a virtual thread and one of these native thread, let's execute that. While it start executing, what it can do is, if it sees any blocking operation, something like calling a microservice or database operation or any IO, it can yield itself from the carrier thread. It can unmount itself. So what happens is, let's say this carrier thread is running and it takes a virtual thread and it's running on top of that, and this virtual thread basically calls a microservice. Now it needs to get the result. It will take some time to get the result, right? So this is the blocking operation, right? So when it sees that virtual thread can yield, it can unmount from a carrier thread, and carrier thread becomes free. So what happens is, when it's free, it can just take another virtual thread and start executing. And the virtual thread that's basically sitting idle in the memory, and it's not wasting our the expensive limited resource that we have. So in a fork join pull, we have a number of native threads. They're always running. They're executing virtual threads. And if we need to stay idle, virtual thread is stay idle, not the native threads. That's not the platform threads. So that's how we get this improvement. So our threads are always working all the time, which is our native threads. And if I need to wait, virtual threads waits. data is available, virtual thread, since it's in the queue, it will get chance again. So, and we can create a millions of them. We don't have a limit on how many we can create. Virtual thread is like just another Java object. I mean, it has all the aspect. It has like a stack. I mean, it has all the functionality that a traditional Java thread has. We can debug and all those things, but it just worked like a short-lived Java object. You ask it to do certain things, it will do. If it sees a blocking operations, it can wait in the JVM. I mean, in the memory. So that's how we got this improvement. I have a quick demo. It's not probably an ideal demo, but I just wanted to make the point. So let me explain this code a bit. What happens is, so we have a this is a dummy call. Basically, it sleeps for 10 milliseconds. Think this is a IO operation or a blocking operation that maybe it calls a microservice, and it takes to get the result, it takes like 10 milliseconds. So what we're gonna do is we're gonna run these applications in virtual thread and as well our traditional threads, which is our in executors, the way we used to do, which is executors, right? We have a thread pools. So over here, we have created thread pools, and the number of threads we're gonna use is the amount of processor available. So the reason we are doing this is basically virtual thread runs on top of a fork-join pool, and fork-join pool usually takes the number of CPU available. It takes the number of thread. Sorry, I'm making it confused. So basically, what happens is the runtime. If we call this method, it will give a number, which is basically the amount of core available in your machine. So we're going to use the same number in our thread pool executors. Just to give you the comparison, it's probably not the ideal test, but just to give you an idea. So in our new fixed thread pool, basically we have, let's say the number of available CPU is 10. So we have a 2-thread pool now. One is a fixed thread pool, which has 10 threads. All of them are natives. And we have a executors, which is virtual threads. Fork-join pool, which also have 10 threads. And this fork-join pool basically execute all the virtual thread. And our native previous new fixed thread pool has 10 thread, but they all basically run those call. Over here we have like 1,000 tasks. So first we're gonna send them to our new thread pool, and our native thread is going to execute them one by one, not one by one, because we have 10 threads, so some of them will be parallel. And over here, so we're going to use virtual threads and the number. And now we will compare the throughput basically. So if we run these applications, I guess I can run these applications. So as you can see, traditional executors took like 1,000 millisecond, and the virtual thread took like 26 seconds. The improvement, the traditional one can improve if we add more threads over here. For example, we use 10 over here, let's say. If we use 100, then it will definitely improve. But if we if we keep on adding more, for example, what if we add 10,000 over here? Then the performance will gradually, go down basically. But over here in virtual threads, even our task is million, it will still comparatively perform better because it's using only 10 threads, the number of CPU availables, and those are always working. So there is less context switching, and there's less waiting. So this is the idea basically. Okay, so there are certain benefits of having virtual threads. virtual threads don't consume CPU while they are waiting and sleeping. They just stay in the memory. Technically, we can have millions of them. And now these are basically cheap. We can have the request for thread style server-side programming easier. It certainly improved throughputs. So, for example, if we go to the earlier image, which is the this one, so all of them can be done by a virtual thread, right? So this database operation can be done by a virtual thread. If we need to go to the Redis, it can be done by a virtual thread, and all of them can be done separately. And on top of that, this whole request can also be done by a virtual thread. If we and we'll have a limited number of platform threads, and all those platform threads will always running, always executing, and they are not wasting our CPU. So that's essentially sum up. If we sum up whole things, it improves our overall throughput. So, and it's a huge improvement in terms of if we really see the benefits, basically. And also with the virtual thread, we no longer need to maintain a thread pool. Maintaining a thread pool is not that easy. It sounds. We have to always tune up, right? We don't know how many threads we're going to put on the thread pool. Is it 100 or 10,000? We always have to test it out and figure it out. In a different settings. So finding the right balance sometimes becomes tricky. But with the virtual thread now, we no longer need to maintain that. That's a huge, benefits. So now I have a different, what do we say? We have a different approach. So earlier, all this problem could be solved by a reactive style of programming, but reactive style of programming had some limitations. And let's say we want to download 10 KMS. If we want to do it with the reactive programming, we can do something like that. And while it does give us the result, the only problem is it has a learning curve. And if you want to debug it, it's going to be difficult. If we want to take a thread dump, it will probably not get anything from there. And if you want to explain this to a junior developer that just came to your team, you will find difficulties. But with virtual threads, you can do something like this. It's a traditional. It's a for loop. It's an imperative. You don't have to explain anything, and it will yield the same result, but it's imperative and traditional, and you got all the benefits that traditional thread have. So maybe so we have two code over here, this one and this one. I would prefer the second one in favor of virtual threads. And since we have virtual threads, we can do this now. Okay. So what are the frameworks currently trying to implement virtual thread? Obviously, Spring Boot is on top of that. They are trying to, I think, since JDK 21 and Spring Boot 3, we can use virtual thread. And there are a few other frameworks that's trying to include virtual threads, Helidon, Nimark, Workers, and many other I have not included here. This slide is a little bit older, but yeah, I have seen many frameworks trying to include virtual threads. If you want to see the benefits from a very high level point of view, think about this is a quite example. I got this from a mailing list. I think it's Java Champion mailing list, or I don't remember. Someone shared this nice example of virtual thread versus traditional thread. So the idea is, let's say you go to a bank and there will be a teller. Think all those teller are basically a thread. So you go to a particular teller and you request to do something, and to process your request, the teller needs to do certain things. For example, he might or she might need to call someone and get result, or wait for an email. And if we stay there, and so basically, while Taylor is doing his work, you are idle there and you are occupied. So both of you are basically occupied, right? Because he's waiting for an email to get, or he needs to get result for someone else. While you are doing this, Taylor is basically occupied, and that's it. Uh, but on the other hand, if the Taylor is a virtual thread, what would happen is, um, while waiting, you can just you can just sit in the bench, and the main thread is, it can serve other customer while you are waiting, and when the result is available, you will get your chance again. So that way, Taylor is always working, serving more users, more customers, and there is no waiting time in the Taylor end. But as a virtual thread, as a customer, you can always sit in the chair and relax. So virtual thread, basically what happens is, when a virtual thread call a IO operation, basically it yells itself and stay in the memory and relax until the result is available, and the main thread is basically continuously working. So, and if we add up those things in a whole, this improves performance, improves throughputs. So now the question gets to be why I named this presentation Tale of Two Cities. Basically what happens is, now we have a two kind of threads. One is traditional, one is virtual. And one, so there's two cities, I would say. So one city is basically the virtual cities or virtual threads, and the other one is our traditional, what we had until we have JDK21. So I just wanted to give a history and context, and this is how we have improved gradually, and this is where we are. And I mean, this is not end of the journey. We'll still have long way to go. For example, there are a few other ideas are going to be implemented in JDK. For example, one of them is structured concurrency. It's not in JDK yet. I mean, it's available. It's a preview feature you can try and check out. But maybe we'll discuss structured concurrency in another session. So yeah, this is the whole session. I don't particularly have anything else, but I can share a few quotes from Ron Pressler, who is the behind the all of this. Basically, what he says is virtual threads are cheap enough to have a single thread per task. Basically, now that we can have a lot of them, one server can in fact serve a lot more users compared to earlier, and it eliminates many of the common issue with writing concurrent code in Java. Basically, if you need a task that you need to do independently, you can just create a virtual thread. You can execute a task, just submit that task to a virtual thread. That's it. And in terms of API, there aren't many. So you don't have to learn a lot. I mean, the learning is basically this: how we are going to use thread pool. So let's say if you need to, traditionally, if you use thread pool, something like that, executors, new fix thread pools. So let's say previously you used this, and you submit task to this thread pool, submit, and you have a runnable. And inside runnable, you submit a task. And this is it. So, and then you get basically, let's say it returns a value which is 10, and you get a future, right? Just to get a future. So I have let's say I have a lot of code like this. Now I want to move into a virtual thread. What do I have to do? Pretty simple, pretty much nothing, except we'll just change this to this method. So we'll just change the executors, which is new virtual thread part executors, and everything remains same. So inside this new virtual thread part task executor, what happens is if you submit, this code will be executed by a virtual thread, and everything remains same. So not a lot of change, and you don't need to use pull anymore. So this is not a pull. This is basically since if we have a lot of code that relied on executors, it's just giving you a new API so that you can migrate easily. So that's all I have. And if you have any questions, feel free to ask. Now is the time. I'll try to entertain as much as I can. But if I cannot, then obviously I'll go and try to figure it out and share it some other ways.
You did have a couple questions, and I will say we're very well represented in our audience today. I see people from Brazil, I see people from Colombia, New Jersey, Missouri, the Netherlands, Switzerland, and we're all over the place, which is just fantastic. So we did have one question that came in that said, can we create a platform thread from a virtual thread? If so, how can we track that newly created platform thread?
That's a good question. That's a good question. I didn't try that, unfortunately. So let me see if we can do that. I mean, if it works. So I mean, I can always do that experiment, right? Let's say over here, if I do create a thread of platform thread, let's say, what would happen essentially? I don't know. Let's see. We figure it out. Right? I mean, looks like. Did we get this result? Okay. So looks like we can create, but that's a good question. How we're going to track it? I would rather ask these questions. Do we need this? I mean, why do we need this? We need to create a platform thread from from the virtual threads. I mean, do we have a use case? If we have a use case, probably. But yeah, it's a good question. I'll probably look into more about it. But right now, I would rather ask question why we need that.
Yeah, there was a comment along the lines of a virtual thread can be pinned to a platform thread, but probably want to avoid that. So that seems good. Another good question here is, do you have some good resources for learning more about threads, how to do it right? And obviously things have changed quite a bit, although the very first recommendation was Brian's book, Java Concurrency in Practice.
Yes, that's definitely, I would say, if you want to learn concurrency, that's probably the Bible of concurrency, and it's still relevant if you want to learn those nuances, how concurrency in general works. You definitely go ahead and read that book, which is Java Concurrency in Practice. Interestingly, I'm also writing a book on concurrency. I'm not sure when it's going to come out, but when it comes out, I'll definitely share with you all. But yeah, Java Concurrency in Practice is definitely a good place to go. And if you want to learn virtual threads, there are plenty of resources already available in the internet. It's just type virtual threads, and you will find a tons of them. And yeah, so the only problem I see while reading some of the earlier books written on concurrency, they start with a presumption that everyone basically says that this is a complex topic. Probably you shouldn't try something like that. But concurrency in general, indeed, a complex topic. But I would say it shouldn't be. It shouldn't stay that complex, right? It should be fun. It could be fun as well. And I personally feel it's a fun. I mean, I can do a lot of interesting things simultaneously, parallelly. I can do a lot of experiments, right? I personally feel concurrency is fun programming.
Yeah, the correct answer to when your book is coming out is always real soon now, for some value for real soon. That's pretty much been my experience in every book I've written. Real soon, real soon.
Real soon, yeah.
So
Yeah.
while I wait to see if any other questions pop up, one thing I was kind of curious about as we're going through your presentation today is, what do you see as sort of the biggest stumbling blocks, confusion points? I think there's a lot of sort of uncertainty, doubt, fear around concurrency. Do you see anything in particular that comes up often when you're working with folks that this is a recurring theme that you see that people struggle with?
So what I see is basically in the industry. So everyone try to be cautious. So let's say JDK is still fresh. I mean, virtual thread is still fresh. JDK 21 came just last year, and so everyone thought process basically, let everyone use, and it matured. I mean, the thought process, it's probably not that matured yet. Maybe wait a year or two, and when everyone join the force, I will join. And other thing is, I mean, migration. For example, if you have a large code base, you cannot always migrate easily. It's sometimes not. It is not related to JDK itself. I personally think, for example, if you want to, let's say, if you have a Spring boot application that's in Spring Boot 2 point something, right, and you want to add JDK 21. So maybe you also want to add other features. For example, if you want to, maybe you want to upgrade Spring Boot itself as well, right? 3, for example. And some library that you use, probably they have some certain things that doesn't allow you to upgrade immediately. For example, in one of my organization, we had a dependency with a library by IBM. So that particular library doesn't work after 11. So and they stopped supporting that library, but we used to rely on that library a lot. Unless we rewrite the entire functionality, we were not able to upgrade. So something along the line can happens. But other
For
than
sure.
that, I definitely want to see. For example, in my current organization, we are all upgrading to JDK 21, and we're doing it, and we're enjoying it, because JDK 21 has tons of new features, not just virtual threads. I mean, other features. So which we are basically enjoying. Yeah, I would definitely suggest try it. Let's see how it works. I mean, I don't see any personally, I don't see any major issue, other than if you have those other dependencies, like as I have just give an example.
Awesome. Yeah, it does seem convincing folks to upgrade their JDK is more challenging than I feel like it should be, but I've certainly run into a lot of that over the last couple of years. So, nature of the beast.
Yeah, but I'm doing this. For example, in my current organization, I'm definitely doing it, and we're
Fantastic.
doing it. We're upgrading all our project to JDK 21, and I'm super excited. So
Awesome.
I mean, perhaps you will also be excited. I mean, you will enjoy using some of the newer cool features that's available in JDK 21, because it's shipped a lot.
All right, we popped another question here. So if I request 1 million virtual threads, will it take more memory? Essentially kind of a microservice space where maybe I don't have unlimited memory, or I'm trying to constrain that for cost. What does that look like?
So I mean, theoretically, it should serve. I mean, for example, I can. The idea is when you are going to use, where you are going to use 1 million threads. I mean, and the main idea is those threads, virtual threads, are short-lived. Basically, what happens is, let's say you have a lot of user coming into your applications. Maybe I'm not sure if 1 million user will come to your application at a point of time, right? Let's say it will gradually improve. But if you have a lot of tasks, most of those tasks are basically short-lived. So I would say, think about a string object, right? Do we care when we are going to create 1 million string? I mean, if we need to create 1 million string, do we think it will gonna, obviously it's going to take a lot of memory. So the concept pretty much out the same, right? Regular, if you want to create a million object, other object, what would prevent you to create 1 million virtual threads, right? It's the same things. Basically, it's going to the use same heap like other regular objects. It's just a thread that gives you certain benefits compared to other object, but in terms of object, they are pretty much same, right? So I don't see. But again, you can try it out, right? Basically, you can do an experiment, see how much memory it takes and requires. So we always say do the experiment.
Well, I think a great spot to end here is Jesper's comment that virtual threads plus structure concurrency equals awesome.
True. I couldn't agree more.
Awesome. Well, thank you. And thanks to all of you for joining us. I really appreciate it. I hope you enjoy the rest of the Java Champions Conference. But for now, we will bid you a good rest of your day. Cheers, everybody.
Thank you. Take care. Bye-bye.